Welcome to the online lecture series on electromagnetic theory by Elias Deepak. In the last class, we have seen the unit vectors in various three-dimensional coordinate systems, and we have also seen their interrelation. In this class, we would like to discuss how a vector given in a certain coordinate system can be expressed in terms of unit vectors in their coordinate system. In future, this would be quite useful for us, where there is a need of transforming how we address a point or how we look at this space. So keeping that in mind, we would like to see how a vector can be transformed from one coordinate system to another. Many of you might have missed the last lecture. Hence, we would just recap the components of those lectures which would be useful in our current module. First thing to remember about these unit vectors is that unit vectors in cylindrical coordinate system are not universal. What we mean by that is, in cylindrical coordinate system, the three unit vectors a rho cap, a phi cap and ah cap are: a rho cap is the projection of the positional vector, a phi cap is the unit vector along the direction of increase in phi, and ah cap is unit vector along altitude. How they differ when compared to Cartesian coordinate system is, the directions of the unit vectors in Cartesian coordinate system, ax cap, ay cap and az cap, are constant and fixed. They are not changing wherever we go in space. The direction of ax cap, ay cap and az cap is constant. But that is not the case for the unit vectors in cylindrical coordinate system. They are space varying. They vary if you move from one point to another point. That we have seen in the last module. So, one thing which we should never forget is that these unit vectors are not universal, and they can be expressed in terms of universal unit vectors. They are nothing but the unit vectors in Cartesian coordinate system. We have seen that last class, where a rho cap is given to you by cos phi ax cap plus sin phi a phi cap, and a phi cap is given to you by minus sin phi ax cap plus cos phi a phi cap, which is constant in cylindrical coordinate system is ah cap. That is same as the unit vector along z axis. This formula here would be very useful for us to convert any given vector into the cylindrical coordinate system. Now, similar is the case for unit vectors in spherical coordinate system. Unit vectors in spherical coordinate system are also not universal. They are also changing with space. Hence, they can also be expressed in terms of the universal unit vectors, that is the unit vectors in Cartesian coordinate system, and they are written as AR equals to sin theta cos phi ax cap plus sin theta sin phi ay cap plus cos theta az cap. That is the unit vector along the positional vector. Similarly, a theta, which is the angle between the positional vector and the z axis, the unit vector in the direction of increase of the angle between the positional vector and the z-axis is given to you by cos theta cos phi ax cap plus cos theta sin phi ay cap minus sin theta. Now, a phi cap, which is similar to the unit vector in cylindrical coordinate system, would be minus sin phi ax cap plus cos phi. So these are the terms which we should be consistent with while discussing vector transform. In a three-dimensional space, any given vector can be decomposed into three mutually orthogonal components. Whatever might be the coordinate system which we are discussing, any three-dimensional vector can be split into three mutually orthogonal components. Now, if it is a Cartesian coordinate system, then the components would be along ax cap, ay cap, and az cap. The magnitude of component along ax cap can be obtained using the operation of dot product, and that is a bar dot. It is denoted as ax. Please note that this ax here is not a vector component but a scalar component. So the vector component along ax cap would be ax. Similarly, the magnitude of components along ay cap and az cap can also be determined using the operation of dot. Ay equals to a bar dot ay cap and az equals to a bar dot az cap. These are the scalar components. Again, vector component can be written as the magnitude and its unit vector. So the decomposed vector a bar can be written as a bar equals to ax cap plus ay cap plus az cap. This idea of representing a vector is much more important to us, as this is key in converting a vector from one coordinate system to. Now, if we are discussing a cylindrical coordinate system, the unit vectors in cylindrical coordinate system are a rho cap, a phi cap, and ah cap. Now, the vector which is decomposed along these directions can be written as a bar equal to a rho cap plus a phi cap plus ah cap, where the value of a rho can be obtained again using the operation of dot product and is performed between the given vector and the unit vector along which we would like to determine the component. That is, a rho equals to a bar dot a rho cap, a phi equals to a bar dot a phi cap, and ah will be equals to a bar dot. Similarly, if we are discussing in spherical coordinate system, where the unit vectors are ar cap, a theta cap, and a phi cap, we can write the vector as a bar equals to ar cap plus a theta cap, and a phi. So what we have done in Cartesian coordinate system and cylindrical coordinate system, AR can be obtained as dot product between A bar and AR equals to A bar dot A theta. A theta would be equals to A bar dot A theta cap, and A phi would be equals to A bar dot A phi cap. Please remember or recollect that A phi here is same as the A phi which we have seen in cylindrical coordinates. Now that we have recapitulated the concepts of unit vectors in all three different coordinate systems, let us now direct our attention towards the problem in our hand, that is converting a vector from one coordinate system to another coordinate system. We have given three different expressions for the same vector in the same space. Now, please remember that the expressions of these three vectors correspond to same vector A bar. And as we have not changed any space, the space is also. Now, because of this, there is bound to be some correlation between those components. We utilize that correlation to convert vector from one system to. Now, consider a scenario where a vector is given to you in a Cartesian coordinate system. A vector decomposed in a Cartesian coordinate system would be looking like this. Now, you are asked to express the same vector in a cylindrical coordinate system. As seen earlier, a vector in cylindrical coordinate system would be looking like this. Now, in order for you to convert the vector into cylindrical coordinate system, you are requested or you are determined in finding out the values of A rho, A phi, and A. So, to determine AR, in order to determine A rho, that is the magnitude of component along the direction of arrow cap, you would like to perform the dot product operation between the given vector and the unit vector of the choice. So this operation would give us the magnitude of component along A. Now, if we substitute the expression which is known to us from the Cartesian coordinate system and you perform the dot product with arrow cap, you remember, can also be expressed in terms of ax cap, ay cap, and az cap. Now, if I apply the distributive property, this is what I'd be getting. This ax would be dotted with this entire vector, ay would be dotted with this entire vector, and similarly az would be dotted with this. After this operation, now here I should be applying one more distributive property where you see ax dotted with ax cap dotted with ax cap would give me 1, whereas ax cap dotted with ay cap would give me 0, because ax cap, ay cap, and az cap are orthonormal pair, orthonormal set. So now the answer would be ax cos phi plus ay sin phi plus az. You have az dotted with ax and ay. The result is, so A rho is the expression which you are seeing on your page. A similar principle can be followed to determine the component along A phi cap. To determine the magnitude of component along A phi cap, I will be again performing the dot product operation with the given vector and unit vector A phi cap. And A bar is given to us in Cartesian coordinates, and similarly A phi can also be expressed in terms of unit vectors in Cartesian coordinates, which we have seen already. Now, once Again, I apply the distributive property and I'd be getting the expression given. Again, you see ax is dotted with ax, answer would be minus sin phi. Ax dotted with ay would be 0. Ay dotted with ax would be 0. Ay dotted with ay would give me cos phi. Again, az with ax would be 0 and az with ay would be 0. So the expression of a phi in terms of ax, ay and az would be a phi equals to minus ax sin phi plus ay cos phi plus az times 0 because of the dot product between that and other vector. Now, similarly, if you are to determine the unit vector, magnitude of the component along AH cap, I would be dotting with AH cap. A bar would be dotted with AH cap. So, AH would be A bar dotted AH. AH equals to this, and once again, you remember that the unit vector AH cap and AZ cap are both one and the same. So I can directly look from this and say that this term would be cancelled out, this term would be cancelled out, and only this term would be remaining. So AH will also be same as. If I rewrite these expressions of A rho, A phi, and AH, they would be first expression of A rho, A phi, and AH. If I write them in the form of matrix, I can see that this form a 3 by 1 column matrix, and ax, ay, az can form another column matrix, and the entries of coefficients between them would form a 3 by 3 matrix. So the matrix would be looking like. Now this matrix is called as transformation matrix, because even if you don't know all the concepts, whatever we have discussed till now, if this matrix is available with you, then you can directly convert a vector in Cartesian coordinate system in the form of a vector in cylindrical coordinate system. This matrix is of utmost importance. But I suggest you not to remember the matrix as such, but to understand how the matrix has been obtained. The observation which you can make from this matrix is similar relation exists between unit vectors. If you go back to the unit vectors of cylindrical coordinate system, you may see that a rho equals to cos phi ax sin phi ay plus 0. This is much similar to what we have obtained in the previous slide. See, that is an interesting observation to make. Consider a scenario 2, which is converse of scenario 1. In this scenario, a vector will be given to you in cylindrical coordinate system, and you are requested to express the same vector in Cartesian coordinate system. That is, now a rho, a phi, and ah are already known to you. You should be determining ax, ay, and a. This is the vector which will be given to you as cylindrical coordinate. As seen earlier, the vector in Cartesian coordinate system would be in this form. Now, same principle, to determine ax, what you should be doing is directly performing the dot product operation between a bar and ax. So now ax is a unit vector in Cartesian coordinate system, whereas a bar is the vector expressed in cylindrical coordinate system. That is in this format. But note that aero cap, A phi cap, AH cap can be expressed in terms of AX, AY and AZ. So if I do so, this entire operation would be expanded in this form. Now again, wherever the unit vector is similar, the product would be the coefficient, and wherever the unit vectors are different, the product would be 0. Similar is the case everywhere. So the expression for Ax in terms of the coefficients in cylindrical coordinate system would be like. Similarly, to determine Ay, what you would be doing is you would be performing the dot product between A bar and Ay. And again, A bar is a vector expressed in cylindrical coordinate system, and the unit vectors in cylindrical coordinate system can be expressed in terms of unit vectors in Cartesian coordinate system, and again perform the dot product operation after applying the distributive property, and this would be the expression for Ay in terms of aero. Now to determine Az would be also requiring you to do the same, but again, as you know that AH and AZ have a direct relation, that they are one and the same. Aero and A phi are orthogonal to AZ. So the answer would be again just A. Now, if I again write the expressions in one place and I try to create a matrix which I have created earlier, now here this is the unknown matrix, a column vector, and these would be my known vectors, and again I'd be forming a 3x3 matrix of coefficient. This is the transformation matrix for scenario 2. Interesting observation which I can make is the transformation matrix obtained in scenario 2, which is this, is just the transpose of transformation matrix obtained in 1. If you can see in scenario 2, this is minus sin phi, and in scenario 1, this is sin phi. When you transpose this, these two would be interchanging, these are zeros, so there will be no difference. The principal diagonal elements anyway don't change. This is just the transpose of transformation matrix in scenario 2. I would like you to pursue the reason behind it. Why is it so? A hint I can give it to you is orthogonal matrix. That's it. I don't want to indulge much further. Let us try to obtain a generalized form of the transformation matrix. That is one matrix which can be obtained for any type of conversion from one system to the other system. Note that whether the transformation matrix we got in scenario 1 or the transformation matrix we got in scenario 2 are particular solutions. They are applicable only for those problems. What I am interested to know is there a way where I can get a matrix which can act as the transformation matrix for any problem of transformation from one coordinate system to another coordinate system. With that in my mind, I move to generalize the expressions of transformation. For that, let us consider the scenario 1 and try to obtain some generalization out of it. The equations for transformation in scenario 1 are, this is the expression for arrow. You see this expression of ax cos phi, ay sin phi and az times 0. How did you get this cos phi, sin phi and 0 can be verified or can be revisited in this. If you see, what you have done is you got ax dotted with arrow, ay dotted with arrow and az dotted with arrow. That has given you this equation. Now, what I would like to do is, instead of finding out the solution as such, I would like to keep this in the form of the vector. So the equation would be looking like this. Arrow equals to ax times of arrow dot ax cap. Arrow cap dot ax cap. Similarly, arrow cap dot ay cap and arrow cap dot az cap. This way, this minus sin phi is the dot product between a phi cap and ax cap. This cos phi is the dot product between a phi cap and ay, and the 0 is the dot product between a phi cap and az cap. Again, the third equation of transformation is of ah, that is ah equals to az. The dot product is in ax and ah and ay both is. So now, if I try to construct a matrix out of it, again, see, this unknown matrix is a 3 by 1 matrix, same here, and the known matrix is also a 3 by 1 matrix contained of ax, ay and az, and this would be giving me a 3 by 3 matrix, the terms which are in yellow braces. So if I construct the matrix, that would be looking like this. Out of this, why I am saying that it is a generalized expression is, if you see this arrow cap is the vector along which the magnitude is unknown, and ax cap is the vector along which the magnitude is known. So your three-dimensional transformation problem will have a 3 by 3 transformation matrix where in each row the dot product would be with the vectors along which the magnitude is unknown, and the columns correspond to the unit vectors along which the magnitude is known. Thus, I make a transformation matrix of 3 by 3. This generalization is not just for any three-dimensional transformation. This can be extended for any n-dimensional transformation. That is, a coordinate system of n dimensions to another coordinate system of same n dimensions. If you are to transform from one coordinate system to another coordinate system, each of n dimensions, then similar such matrix can be generated where the rows correspond to the unit vectors along which the magnitude is not known, and the columns correspond to the unit vectors along which the magnitudes are known. Now, let's check for the validity of the generalization drawn. If I are to say that the generalization is universal, then obviously that must be applicable to the converse of the scenario 1, that is a scenario 2. So if I construct a matrix for the transformation problem in scenario 2, where the magnitudes A-rho, A5 and AH are known, whereas AX, AY and AZ are not known. I would be constructing a 3 by 3 matrix. Where the rows correspond to AX, AY, AZ. The columns correspond to A-rho, A5 and AH. Now, the way it would be looking like is this. You may see that here the rows correspond to AX, AY, AZ and the columns correspond to A-rho, A5 and AH. If it is not visible, evident to you in the earlier observation made, it must be evident to you now that the matrices obtained for the problem in scenario 1 and the problem in scenario 2 both are transposed to one another. Not just that, they are also inverse to one another, as they must be. And if I verify that performing the dot products mentioned in the matrix, I will be getting the same matrix which I have gotten earlier. So thereby I can conclude that generalization is valid for scenario 2 as well. This is an assignment which I request you to do. Please take a screenshot of it and submit that in your Google Classroom. Thank you. We'll meet again in the next module.